Right. As I said, the next part of this chapter focuses on what happens when a charge moves in a magnetic field. Okay, what are the effects of magnetic field on charges? Okay. Have you all, have you ever heard of something called aurora formation?
Yes, sir.
What is it?
Sir, the sky has like different colors. Uh,
Ha. You see some colorful curtain-like patterns in the sky at some places on Earth.
Polar regions, right, sir?
Ha, especially in the polar regions. Yes, yes. Can any of you tell me how that happens?
Has something to do with the Earth's magnetic field.
Correct. It has something to do with the Earth's magnetic field, and Earth's magnetic field is strongest near the poles compared to other places on Earth. Yes, it has to do something with the magnetic field. Can you give any further explanation why it happens? Because Earth's magnetic field is always there, but aurora will not always be seen. It's seen only sometimes. Why?
so
Okay,
there are solar flares happening sometimes. So like,
correct. Anyway, fine. So basically, what happens, as Rishi was saying, we or not we come across, it so happens that the sun sometimes emits particles into the space around it. Okay, we call that as a solar flare. Now, some of those particles will travel towards the Earth as well. Okay, sometimes they'll be significantly large in number. They'll be having significant amount of energy also. Okay, so when particles from the sun, high energy particles from the sun, you don't need to know what exactly there. It's called plasma. What exactly it is made up of and all, you put it aside. When high energy particles from sun come towards the Earth, okay, you can imagine this as the axis of rotation of the Earth in this case. So this is the North Pole, this is the South Pole. So imagine particles from the sun. This diagram is not to scale, but imagine the particles moving this way. Those particles which move near the poles of the Earth, okay, they experience the strongest magnetic field of the Earth. Fine. Earth's magnetic field we'll discuss a little while later, but Earth's magnetic field is strongest near the poles. And due to that magnetic field, what happens? These particles, which are usually charged, okay, they deviate from their original path. They don't go along a straight line like this. Okay, due to the magnetic field, what happens? The particles, they kind of get trapped and get deviated from the path or the direction in which they are originally moving. So basically, they get pulled into the Earth's atmosphere. Due to the Earth's magnetic field, by the Earth's magnetic field, they get pulled into the Earth's atmosphere. And when some other particle enters into our atmosphere or Earth's atmosphere, that other particle will have to lose energy because of collisions or whatever. And that energy, those high energy particles, when they lose energy, that energy is released, some of that energy is released in the form of light. Okay, that is what appears to us as aurora, like these curtains of colorful patterns. So based on what you learn in this chapter, you will be able to answer why charged particles get deviated or how charged particles get deviated in magnetic fields and all. You'll learn in this chapter. So suppose a charge Q moving, or let's say a charge Q moves with a velocity v in a magnetic field B. Okay, then it is found that when a charge moves in a magnetic field, it experiences a force. Fine. And they notice some properties of force on a charge in a magnetic field. What are the properties? First, this force never changes the speed of the charge. It does not affect the speed with which the charge is moving. Then what does it do? How did they find out that there's a force acting on it? It can only change direction. Okay. Now let's recollect one small idea from what you learned in 11th class. Suppose an object or a particle is moving in this direction with a velocity v. Now, depending on the forces that act on it, depending on the net force that acts on it, it could have an acceleration in some direction this way. Okay, let's say the object has an acceleration in this direction. You can resolve acceleration into two components. One component of acceleration parallel to velocity. Can any of you tell me the name given to that component of acceleration parallel to velocity?
Tangential acceleration, sir.
Good, tangential acceleration. And one component of acceleration perpendicular to velocity, and what is that called?
Radial acceleration.
Radial acceleration, correct. Fine. So whatever acceleration an object has, you can always resolve it into two components, one along the velocity and one perpendicular to velocity. The component along velocity, which is tangential acceleration, it can only change speed. It can't change the direction. It can only change the speed of motion of the object. It can make it go faster if it's in the same direction. In case it's in the opposite direction, for example, if the acceleration is this way, then its component along velocity will be opposite to it. Perpendicular component will be like this. So if an acceleration component is there opposite to velocity, then it slows down the particle. So remember, tangential acceleration can only change the speed, whereas radial acceleration can only change direction of motion of the object. It makes it deviate from that path. It can make it turn to the left, right, up, down, whatever it is, it won't allow it to continue straight. Now, magnetic force was found to change direction but not change the speed. That means magnetic force only acts perpendicular to the velocity. It does not act parallel to velocity. So based on these two facts, okay, we can conclude that the magnetic force, I'm writing it as FB, force due to the magnetic field, okay, only acts perpendicular to the velocity of the charge. It does not have even a component in the parallel direction. The force completely is perpendicular to velocity. Next, experimentally, it was also found that the magnetic force is also perpendicular to the magnetic field. Okay, so it's perpendicular to the velocity of the charge. It's perpendicular to the magnetic field in which the charge is moving. Now, based on these two, we can conclude that the magnetic force, it's perpendicular to both velocity and magnetic field, which are vector quantities. So force is perpendicular to two other vectors. And if you want a direction perpendicular to two other vectors, you need to take their cross product. So magnetic force is along or exactly opposite to the cross product of these two vectors. Because I'm sure you all know this, the cross product of two vectors is perpendicular to both the vectors. Okay. And suppose there are two vectors in this plane, the plane of your screen. Perpendicular to this screen could be perpendicular out of the screen. It could also be perpendicular into the screen. So there are always two possible directions perpendicular to two given vectors, right? So if one of them is the velocity vector, the other is the magnetic field vector, the direction out of your screen is perpendicular to both of them. The direction into your screen is also perpendicular to both of them. And the magnetic force could be along any one of these directions. Okay. And then they also found that magnetic force depends on the charge of the particle. Stronger the charge, stronger the magnitude of the force. They found that magnitude is proportional to charge. And they also found that positive charges experience force in one direction, negative experience in another direction. Okay. So they put all of this together and they found one relation which explains all these, okay, and connects, and you can express the force in terms, using that equation, okay. And the force on a moving charge is given as Q V cross P. Okay, so based on all the observations, they arrived at this formula, which gives the magnetic force on a moving charge inside a magnetic field. So let's understand how to apply this formula. Basically, this can help you calculate the force on a moving charge. First of all, if you want the magnitude of this force, you will have to take the magnitude of the charge. And then, can one of you quickly tell me the formula for V cross B or A cross B? Magnitude of A cross B.
AB sin theta.
AB sin theta. So here it becomes VB sin theta, where what is theta?
The angle between A and B.
Where theta is the angle between, in this case, velocity and magnetic field. So how much force the charge experiences depends on the way it is moving inside the magnetic field. Just because charges are same doesn't mean they experience the same amount of force. Okay. And why did I keep modulus to Q? Because charge could be positive or negative. You have to use this vector equation, you need to substitute, to get the vector force, you need to substitute charge with sign. Okay, but if you only want the magnitude, then only substitute magnitude of the charge. So this is the magnitude of the magnetic force on a charge, qvB sin theta. And then if you observe the equation, magnetic force as a vector is along V cross B if Q is positive. And it is opposite to V cross B if Q is negative. Okay, that's why it is important to substitute the charge along with the sign. Okay, answer this question quickly. Can one of you tell me the direction of Earth's magnetic field? What is the direction of Earth's magnetic field? Or field lines, from which pole to which pole do they point?
Sir, is it from North Pole to South Pole?
Outside the Earth, or last class we discussed the field lines of a bar magnet. Outside the magnet, the field lines are from north to south. Inside, they are from south to north. Okay. So actually, this is the field line pattern, and not just in 2 dimensions. You have to imagine this in 3 dimensions all around the Earth. Okay, that is how the field lines point actually. So you can see that, like, forget this magnet. For the Earth, this is the North Pole, and this is the South Pole. Just a moment. Geographic North, geographic South. What have they shown here? One second. Yeah, so if you suspend a bar magnet, North Pole points towards north. Usually, when you release a dipole, okay, let's talk about electric dipole. When an electric dipole is freely released in a uniform electric field, which way does it settle? Which is its stable equilibrium position? Let's say this is the direction of electric field and you release a dipole in it. How is it finally going to settle?
So the positive end will be with the electric field.
Huh. So this position where the dipole moment is parallel to the electric field, minus q here and plus q here. This is the stable equilibrium position of the dipole. So dipole settles in the direction of field. Now, what do we know about magnets? We know that when they are freely suspended, they settle in the north-south orientation, and the side which points towards the Earth's north is the north pole of the magnet. Okay. So if a magnet is released somewhere here, magnetic needle, it will settle like this, with its north pole actually pointing towards the Earth's north. Fine, that means the field must be this way. Okay, they are from Earth's south pole to the Earth's north pole. Okay, for the magnet, they are from north to south. That's fine. But in terms of Earth's north and Earth's south, if you talk, the field lines, Earth's magnetic field lines, are from the Earth's geographic south to the Earth's geographic north. The arrows they have shown in this diagram are correct. It's like this. So Earth's magnetic field lines point from south to north. Geographic south to geographic north. Okay. Now try to answer this question. An electron is moving towards east. What is the direction of magnetic force on it? Due to the Earth's magnetic field. Electron is moving towards east means the velocity is towards east, and you know electron is a negatively charged particle. Consider all those factors and tell the direction of magnetic force acting on it. Any answer? The force, the magnetic force on a charged particle is given by F is equal to qv cross B. Q, the sign of Q must be considered. And then the direction of V cross B also matters. So think based on those lines. Okay. Seshank, you tell me, velocity is in which direction in this question?
East.
East, clearly. Let's assign those directions first. Assume this is east, north. These are geographical directions, northeast, west, and south. Velocity is this way. Earth's magnetic field is in which direction?
North to south. South.
South to north. They are from the geographical south to the geographical north. South to north. So Earth's magnetic field lines are in this direction. B is this way. Okay. If V is to the right and B is this way, I can't use right and left. V is towards east and B is towards north. What is the direction of V cross B? Anyone?
Like it will be out of the screen towards us.
On the screen, if you see, it is out of the screen, correct. But in real life directions or daily life directions, how would you mention that? How would you specify
Like
that?
above the surface of Earth.
Like,
Like from the center of the Earth to above. Like,
so you are saying vertically upward like this.
yes, sir.
Correct. See, remember, north, east, west, south are all horizontal directions. Okay. If you are facing east, let's say you are watching the sunrise. So east is in front of you, then to your left will be north. They are all parallel to the ground. Okay. Upward is not north. Upward is upward only. The sky is upward. That is not north. Okay. North, okay. East, north, west, sorry, east. To the left you have north. To the right you have south. Behind you will be west. They are all horizontal directions. Okay. Now we need direction of V cross B. V is along east, B is along north. So suppose east is in front of me, north will be on my left. Okay. So V towards east, B towards north. V cross B, my thumb points upwards. So V cross B is in the upward direction. If V cross B is upward, and we know that a charge of an electron is negative, that means the force it experiences will be downward on the electron. Okay, so this visualization and getting the direction of cross product, you have to be comfortable with. Is this clear to all of you? Any doubts in this? Okay, fine. So basically this force is what causes aurora formation. Okay. The energy, the particles that are released in solar flares, usually they are charged particles. Okay. So when they enter into the Earth's magnetic field, the force acting, the magnetic force acting on those charged particles, it deviates them away from their path. They are going in a straight line path like this. They get deviated. You can visualize it like this. Let's imagine the Earth's magnetic field. Magnetic field lines. See, I'll draw one field line in green. It goes from south, kind of like this, to the north. Outside the Earth, that's the field direction. So exactly at the North Pole, the field line is directed downwards. South Pole, the field line is directed this way, out of the Earth. Okay, North Pole, the field line is into the Earth. It's like this. Now charged particles move this way, straight from the sun towards the Earth. So you can see that velocity is in one direction, magnetic field is in another direction. Then their cross product will be non-zero. The charged particles will deviate. Okay, and some of them get pulled into the Earth's atmosphere. Instead of going straight that way, they get deviated towards the Earth. That is what releases the energy. I mean, after that, they release the energy. Due to collision with other particles in the atmosphere, they lose that energy. Okay. So we know what force a charge experiences when it enters into or when it moves inside a magnetic field. Now the expression for the force, as we just discussed, is Q V cross B. Now one of you tell me, see, this force anyway does not change speed. It can only change direction because it's perpendicular to velocity. When is this force zero? When will
when V and B are in the same direction.
When V and B
Are in the same direction.
are in the same direction. Yes. We know that the magnitude of the force is Q VB sine theta. So whenever sine theta is 0, the force becomes 0. And for what angles is sine theta 0? Theta should be 0 degrees. That means velocity is parallel to the magnetic field. So when a charge moves in the same direction as magnetic field, it won't experience this force. Next, when velocity is exactly opposite to magnetic field also, in that case, the angle becomes 180 degrees, sine 180 is also 0. So basically, when velocity and magnetic field are parallel or anti-parallel, the force becomes zero. The charge won't experience any effect of the magnetic field. But in all other cases, it will experience. Okay, so let us discuss those other cases now. And what happens to the charge due to this force? So motion of a charge in a magnetic field. First case, when velocity is parallel to the field or exactly opposite to field, the field shows no effect on it. The magnetic force becomes zero. We know that. Second case, interesting case actually, when the velocity is perpendicular to magnetic field. Let's discuss this in depth. First, we know that the force is perpendicular to velocity. It's only a radial force, not tangential. It makes the object change direction. Let's find out how much force acts. The magnitude of the force is magnitude of the charge VB sine theta. In this case, theta is 90 degrees, sine 90 is 1. So the force magnitude becomes qvB. Okay, when velocity is perpendicular to magnetic field. Only in that case. In other cases, it will be less than this, because in other cases, sine theta will be less than 1. Only for one angle between 0 and 180, sine theta is equal to 1, that is 90 degrees. Okay. So when velocity is perpendicular to magnetic field, the charge experiences the strongest amount of magnetic force. Okay, so they can ask you a question like this also. Anyway, simply based on angle, you can answer, not a big deal. Now we know this force acts perpendicular to its velocity. That means it behaves as a radial force. You can even call it as centripetal force. Okay, a force acting perpendicular to velocity makes an object turn. That is what we call as centripetal force, radial force or centripetal force. Okay, first using this formula, F is equal to qvB. Derive the dimensional formula of magnetic field, all of you. If you remember, we avoided this. We discussed the unit of magnetic field, Tesla and Gauss, but we didn't discuss its dimensions because we didn't have a convenient formula for it. Okay, but from this formula, derive the dimensional formula of magnetic field, all of you. Any answer for dimensional formula of magnetic field? Okay, F is equal to qvB. So the dimensions of B will be dimensions of F divided by dimensions of Q and dimensions of V. Dimensional formula for force, anyone?
ML
T power minus 2 divided by charge.
It is q equals to I into t means A into t.
Charge is current multiplied with time, so it becomes AT. Velocity? LT power
LT
minus
power
1.
minus.
Okay. T power minus 1 cancel, L and L cancel. So the dimensional formula for magnetic field will be M A to the power of minus 1, T to the power of minus 2. I got one answer as Mi to the power of minus 1. You can call it I, not an issue. And T power minus 2 it will be. Okay. From this we can write its basic unit also. M is mass kg per ampere per second square. This is what we call as Tesla. Fine. Next. When velocity is perpendicular to magnetic field, we know the force magnitude is qvB. Let's imagine a situation like this. Assume there is a uniform magnetic field in space. Cross indicates a direction into the page or into your screen. So assume there's a magnetic field directed into your screen like this. It's uniform, means it has the same strength and direction everywhere. Consider a charged particle. Assume it's a positive charge. Moving towards right. Okay, in this case, clearly velocity is to the right. At this moment, it is to the right. Magnetic field is directed into the screen. One of you quickly tell me the direction of V cross B.
It will be above, sir. Like it will move up.
Upward. Okay. Velocity is in the rightward direction. Magnetic field is into the screen. So keep your right hand fingers along velocity. Curl them into the screen. Thumb will point upwards. Or you could do this also. Place your thumb along velocity. Okay. And place your right hand fingers along the direction of magnetic field. Now, okay, I'm explaining from your point of view. Does this pen point to the right or to the left as seen by you?
Right, sir.
Right. Okay. So this is velocity. Magnetic field is towards me, away from you, so towards me. So what I'm asking you to do is, this is my right hand. Okay, fine. So I'm asking you to place the thumb along the velocity and the fingers in the direction of magnetic field. So fingers will be towards me. And which way is the palm pointing? Upward. That is the direction of cross product. You can do it that way also. And that is what we have been doing when we applied ideal cross B, Biot-Savart law and all. We place the thumb along the current and make the fingers point along the position vector. The palm shows the direction of magnetic field. Okay. So for ideal cross R direction, we used to use that. You can use that for V cross B direction also. So thumb in the V direction and fingers in the B direction. Palm will show you the force direction. So in this case, the force is upward, this way. Right. We know the magnitude of the force qvB. Now, object is moving in the x direction, particle is moving in the x direction, force acts in the y direction. So what happens? It deviates, it turns that way. So the next moment, the particle's position may be somewhere here, but its velocity will now be directed somewhat like this. It will be tilted. Why? Because there was a force acting that way. Magnitude of velocity won't change, but the direction of velocity will change. Okay, the orange vector is the force vector. Now, next moment, if you see, velocity is now at an angle like this. Magnetic field is still into the screen. So now if you do V cross B, along that second green vector, you place your thumb, fingers into your screen, then the palm will now point like this. This is the direction of force now. The force rotates along with the velocity. It should be perpendicular to velocity, no? So as the velocity vector rotates, the force vector also will rotate. Okay. And you will notice that both these force vectors, they point towards a common point. They're directed towards a common point. Of course, two arrows will definitely be directed towards a common point. But if you look at it at some other instant also, next moment, the charged particle may be somewhere here. Velocity may be directed this way. okay, rotates further and directed this way, then if you visualize the force, you will see that the vector, the force vector, will again be pointed or directed towards that point itself. So when velocity is perpendicular to magnetic field and the magnetic field is uniform, that is very important. This magnitude qvB will be uniform, means the same amount of force. Amount means magnitude, not direction. The same magnitude of force always acts on it, and it is always directed towards a particular point. Effectively, what happens to the object is it ends up moving in a circular path. That force, the magnetic force, acts as a centripetal force now. That is what happens. Okay, so if an object or a particle has a velocity perpendicular to a magnetic field, and that magnetic field is uniform, same strength. Why is that important? For an object to follow a particular radius, the centripetal force should have a magnitude of v square by r. Okay, that is the magnitude of centripetal force needed for an acceleration, sorry. Force is mv square by r. That's the formula for centripetal force. Now here the speed is not changing anyway, and the magnitude of force also won't change if field is uniform. If speed doesn't change, magnitude of force doesn't change, mass anyway doesn't change, then radius remains fixed. And that means it follows a circular path. Suppose magnetic field is different at different points, then the force magnitude will be different at different points. And if force magnitude is different, radius will be different. The object won't move in a circle. It can move in a curve, but that curve won't be a circle. Okay, these conditions are also very important. Fine. So it ends up moving in a circular path like this under the influence of the force qvB. Okay, B has to be uniform. If it's non-uniform, then depending on the way the field changes only, you can tell how the particle moves. Okay. And for it to complete the circle, the magnetic field should exist at all those points. If the magnetic field exists only at some points, like let's say on this side there is magnetic field, the other side there is no magnetic field, then it can't move in a circle on the other side. Okay, the field is needed to exert the force which is needed to keep it on that circle. Right. Okay, so F is equal to qvB acts as the centripetal force now. And we know the centripetal basic formula for centripetal force is mv square by r. Therefore, simple calculations, qvB can be equated to mv square by r. V gets cancelled. You get r is equal to mv by qb. What do we call this? This is the radius of the circular path which the charge follows when it is inside that uniform magnetic field moving perpendicular to it. Okay, have any of you heard of an instrument called a mass spectrometer?
Yes, sir.
What does it do?
So like depending upon the m by q ratio, it decides the radius of curvature like of the.
Why
like
do
the
you want to
particle.
decide the radius of curvature of the particle? It actually does the reverse. Depending on the radius, it calculates that m by q ratio, and when q is known, it tells you the mass of the particle. So mass spectrometer is something which is used to measure very small masses, like masses of ions, or maybe fundamental particles also, proton mass, electron mass. Okay, such small masses can be estimated using a mass spectrometer, and that instrument uses this idea. So basically what happens inside that instrument, I'll just give you a rough idea. A stream of charged particles, okay, is released into the instrument, and the instrument itself sets up a magnetic field. Okay, so we know the speed with which these charged particles are introduced. We know the magnetic field that exists inside. We know the charge of these particles. Then based on how they revolve, we can estimate the mass of those particles. Okay, actually it combines ideas from electrostatics as well as magnetism. How do you project a stream of particles? Have any of you heard of something called an electron gun? Okay.
Yes, sir.
What does it do? It shoots electrons, but how?
Sir, like there will be two fields, like magnetic field and electric field, sir.
Okay, then
Like as it passes through it,
Hmm.
like it sir, just a minute, let me think. Like I'm getting that idea, but
okay. See, for an electron gun, magnetic field is not necessary. It has to shoot electrons, means it has to project or release electrons at high speed. Electrons are charged particles. How do you give speed to charged particles? Make them go through a potential difference. Okay. So basically in an electron gun, there will be two electrodes having a high potential difference between them. If you just introduce electrons, due to that potential difference, the electrons will get pulled. Potential difference is there, means field is there. If field is there, it gives energy to those electrons. And then they come out of that electron gun. So using a similar idea, you can release charged particles with some required speed. Okay, actually there the calculation would be qV, charge multiplied with the potential difference, is the kinetic energy of the particles. So depending on how much potential difference you apply, you can tell with what speed the particles are going to come out. Okay, or something like that. You MV ratio, MV, that product you can find out, or something like that can be found. And then this calculation using the radius and all, combining these two equations, the instrument can estimate the mass of those particles, fundamental particles. Okay. Yes, you are saying something about a velocity selector. Velocity selector is different. Velocity selector selects charges moving with a particular velocity. It doesn't give them that velocity. Electron gun gives the velocity to the electrons. Okay. They are different instruments. We'll discuss. For an electron gun, you don't need a magnetic field. You only have to create a potential difference. That is an electric field that gives energy to the charged particles. Okay. So yeah, when a charge enters into a uniform magnetic field, or when a charge moves inside a uniform magnetic field perpendicular to it, it ends up moving in a circular path. And see, notice the orientation of the circle. In this case, which way is the magnetic field pointed? Like the one that you see on the screen, which way is the field pointed?
Into the screen.
Into the screen. Let's call that as the Z direction. Then the circle is in which plane? Circle is a planar geometry. It's in which plane?
XY.
XY plane. Correct. A particle which is moving inside a magnetic field executes circular motion in a plane perpendicular to the magnetic field. If magnetic field is in the Z direction, the circle in which it moves will be in the XY plane. If magnetic field is along the X-axis, the circle in which it moves will be in the YZ plane. So it's like that. Because it has to be perpendicular to velocity and magnetic field, it ends up being like that. Okay, so this is the radius with which the radius of the circle in which the particle moves. Next, we know that magnetic force cannot affect the speed of a particle. It changes its direction, and when velocity is perpendicular to magnetic field, the particle moves in a circle. So basically, this is circular motion with constant speed. Velocity is changing because direction is changing, but speed is constant. What do you call circular motion with constant speed? Circular motion with constant speed.
Uniform circle.
Uniform circular motion. The speed remains constant. So it is uniform circular motion. And in uniform circular motion, the particle always takes the same amount of time to complete one revolution. Okay, that's called time period of revolution. So we can derive time period of revolution. Time is basically distance divided by speed. So to complete a revolution, the distance that the particle has to move is 2 pi r, divided by the speed is v. Now we know that R is equal to mv by qb. So R by V becomes m by qb. Substitute that here. Time period becomes 2 pi m by qb. Another interesting result. The final formula that you see for the time period, 2 pi m by qb, what's interesting is that it is independent of the speed of the particle. Because basically what happens, if the speed of the charge is less, here, if the speed is less, the radius would be less. So it's a small circle and it will take some time to complete that circle. If the speed is more, the radius would also increase proportionately. It will still take the same time to complete the circle. Okay, so that is why the time period is independent of speed of projection, speed with which the particle moves inside the magnetic field. Okay, and since we are talking about circular motion, we can even talk about angular velocity. Can one of you tell me how linear speed, or generally speed, and angular speed are connected in circular motion? How
V
are
is equals to R omega.
correct? V is equal to R omega. Therefore, omega becomes V by R. Now, R by V was m by qb. So, V by R becomes qb by m. That's the angular velocity with which the particle revolves in the magnetic field. Okay, this will help you in solving questions based on how much the angle rotates, how much the particle rotates. They may ask you, like, in a certain duration of time, how much does it deviate? How much does it turn? By what angle does it turn? So if you know angular velocity, you can answer such questions. Okay. Fine. And because the particle takes the same amount of time to complete the circle every time, we have defined a time period for it. Inverse of time period is what you call frequency of revolution. So it will simply be qb divided by 2 pi m. Okay. Questions based on all this, we will discuss in tomorrow's class. For now, you just remember that we have discussed about the force that magnetic field exerts on a charged particle, F is equal to qv cross b. What happens to the particle due to that force? It only changes direction, it never changes the speed. This force cannot change the speed. Other forces can change maybe, but not this. Okay. Then we discussed what happens if the velocity is parallel to magnetic field or exactly opposite to it. The magnetic field shows no effect. Then we discussed the other case in detail. When velocity is perpendicular to magnetic field, first, the magnitude of the force becomes qvB, where q is the magnitude of the charge. And because it acts perpendicular to velocity, it behaves as a centripetal force. So if B, the magnitude of the magnetic field, is same everywhere, the magnitude of this force will be same everywhere, and it will move along a curve of uniform radius. A curve of uniform radius becomes a circle. So if B is uniform, it ends up moving in a circle. We derived the radius, angular velocity, time period, frequency of revolution along that circle. Okay. So tomorrow we'll look at problems based on this. Some cases where there is magnetic field everywhere, some cases where magnetic field extends only up to a certain distance, some cases where there is one magnetic field in half the circle, another magnetic field on the other side. Okay, we'll discuss cases like that. Okay, thank you all. I'm closing this session here. We'll continue tomorrow.
Thank you, sir.
Tomorrow we'll have a, okay, wait. Is it possible to attend class from maybe 5 to 6:30 tomorrow? Can you all attend?
Yes, sir.
Seshank, what about you?
No, sir. I will return from school only if I.
Okay, fine. Okay, if not tomorrow, like if in case it's not possible for me tomorrow, then I'll take the class on Sunday.